So we'll start with the branching group of instructions before we do further programming. Fine. So the first instruction in this group is jump address. JMPADDR. So this is your instruction, jump address. Now what does this instruction do? It will basically load the program counter and what will it load the program counter with? It will load the program counter with the address that is actually specified here. Now we know that program counter basically keeps track of the instructions from where the next instruction basically takes place. So if the program counter is being loaded with this address, so that means the next instruction will start, so that the next instruction starts from the particular address. So the address that's being specified here, from there the next instruction will start. If in a normal routine, whatever was the address, it will bypass that and it will directly jump to that address location, to the new address location, and start executing programs from there. So the macro RTL, you can simply write the PC is loaded with the address. And regarding the number of so jump will take a 1 byte. Address is a 16 bits, sorry, so that means actually 2 bytes. So you have a total of 3 byte instruction. So this instruction will consume 3 bytes of memory. And regarding the machine cycles, you have 3 machine cycles also. As you know, the first machine cycle of any program, of any instruction, is the opcode fetch machine cycle. In this case you have address, and address is 16 bits, so it has to be read in it will take 2 machine cycles to read the complete address. So memory read machine cycle and memory read machine cycle. Fine. And then you have moving on, therefore you have 10 T states, 4 of the opcode fetch machine cycle, 3 of the memory read machine cycles. With 10 T states, the total execution time will be 3.2 microseconds. Fine. And it has no variation, it exists only as itself, and therefore you can write an example. You can write any example, you can jump to any address. Say for example we are jumping to address 3300. Fine. So this is your regarding the flags, no flag affected. And regarding the addressing modes, for the source the address is actually given, so it is direct addressing mode. And for the destination, you have been, we do not exactly know the nature, but we can say that it is implied, and the microprocessor will jump to a specific location implied by the address of this microprocessor. Fine. Then you have the machine cycles. As I told you, there will be 3 machine cycles: the opcode fetch machine cycle, the memory read machine cycle, and then you have the memory read machine cycle. You have two memory read machine cycles and one opcode fetch machine cycle. So this is your opcode fetch machine cycle. Fine. And in the T4 state of this JMP ADDR becomes equal to 1. So this is your opcode fetch machine cycle. Then you have the memory read machine cycle. You have two memory read machine cycles. So what will happen in the two memory read machine cycles is, in the first memory read machine cycle, the lower LSB, the lower significant byte of the address will be read, and in the next memory read machine cycle, the most significant bit of the memory read of the address will be read. Fine. So you have two memory read machine cycles in this case. In the first memory read machine cycle, the LSB of the address will be read. In the second memory read machine cycle, the MSB of the address will be read. So this is your memory read machine cycle that we have actually seen previously also. Now there is, yes, the PC is being loaded onto the address bus in the T1 state. The PC will be incremented in the second. In the third, this thing here, it is not T here, it will be Z now. Right. So this is memory read machine cycle 1, and similarly you will have memory read machine cycle 2. So in the memory read machine cycle 2, again the same. In the T1 state, the program counter will be loaded onto the address bus. In the T2 state, the read instruction will be enabled, program counter will be incremented. Whatever is on the address bus will be relocated onto the address or onto the data bus. So this is your memory read machine cycle number 2, and in the T3 state, read instruction will be enabled, 87 to 80, it will be, this thing will go to W. Now you actually have in the memory read machine cycle 1, the least significant bit of the address was read, and that was stored in Z. In the second memory read machine cycle, the most significant bit of the address was read, and that was stored in W. So simultaneously, so in this, now we have the entire address read and stored in WZ. This WZ will be loaded onto the program counter in the memory read machine cycle. Fine. Because this is what the instruction does. This is what the jump instruction does. The jump instruction basically loads the program counter with the specified address, and this specified address is now being loaded onto the program counter. So whatever was written here earlier, that will be overwritten, and whatever address is now specified with this instruction, that will be loaded onto the program counter, and the next instruction will now start from that particular address, not from the next address location. So we have actually done the programs in the last session, and you saw how sequentially the programs are carried out, how much space each instruction takes up, and instead of loading the address instead of loading the program counter with the next memory address, this will be loaded with a specific address from where the instruction has to begin. Fine. So these are actually used in case of modular programming to call on to a routine, a subroutine, so that we can actually directly start execution from that particular location. So this was the first instruction that was in this branching group, that was jump. The second instruction in this branching group is jump conditional. So same, it again, the program counter is loaded with the address, with the specified address, so that next instruction starts from that particular address. So that next instruction starts from that particular address. The difference here being that only if the condition is true. Fine. So say for example, these are our memory locations at, say for example, this is n, this is therefore n plus 1, this is n plus 2, this is n plus 3. So at n we'll write the opcode of jump conditional, whatever will be the opcode of this, and at n plus 1 we'll start writing the least significant bit of the address, n plus 2 we'll be writing the most significant bit of the address. Fine. And at n plus 3 there will be some another next instruction. So once and there is somewhere down the line there is this address ADDR. Now if the condition is true, if while executing this program LSB, MSB and MSB, if the program finds fit that the opcode, that the program is the condition is true, then what happens is the next instruction will start directly from here. Fine. The program will jump to this particular address location and instructions will start from there. If the condition is not true, what happens is n plus 1, the condition is actually checked at in memory read machine cycle number 1, and in the memory read machine cycle 1 we'll only have read so far the LSB of the program. So directly it will see that if the condition is true or not, then it will jump to this location and start the next instruction. So this is the jump instruction. So if the condition is true, then it will jump to the address location. If the condition is not true, it will actually carry on its routine program and move to the next instruction in the specified program. So the macro RTL of this can be written like this. So you actually have a condition. It can be true or it can be false. In case it is true, the program counter is actually loaded with the address. That's actually this address specified here. If it is false, the program counter will be loaded, but with the address it will be loaded with this address. That is the normal address that should have been written onto the program counter, so that normal execution of program continues. Fine. So this is your jump conditional. Now regarding the rest of the properties of the system of this instruction, it's a 3-byte instruction. It has again 3 machine cycles. If true, if it is false, in case of false, there will be only 2 machine cycles. As I said to you, in the second machine cycle only, in the first memory read machine cycle only, the condition is checked. The condition will be determined whether it is true or false. So if it is false, we do not need to move on to the third machine cycle. That's another memory read machine cycle. We know there are 3 machine cycles in this case. One is the opcode fetch machine cycle, You have one memory read machine cycle to read the LSB of the address, and you have another memory read machine cycle to read the MSB of the address. So once you are actually reading the LSB of the address, then only you also check simultaneously the condition. If the condition is true, then this machine cycle will also be executed. If the condition is false, we do not need to load the address. We can stop this machine's instructions and move on to the next instruction. So accordingly, you can either have 10T states or 70 states depending upon whether the condition is true or false. Accordingly, you will be having execution time of 3.2 microseconds or 2.24 microseconds, and there are actually 8 variations of this jump conditional. And what are those variations? Those variations are J, Z. Examples of this: JZ address. So you can have any address. JZ means if 0 is set. JNZ, jump if 0 is not set. So these are the conditions that we need to check. Jump if carry is set. JC, JNC address. These are 4. Jump parity, odd parity, even parity. So we actually know that there are so these are your different variations: JZ, JNZ, JC, JNC, JPO, JP, JP, and JM. No flag affected. Addressing mode for the source and for the destination. For the source, again, it is direct. For the destination, it is implied. And the micro RTL, like we did in case of same as in case of jump address. Only difference being is you have the same opcode fetch machine cycle, you have the same memory read machine cycle, same memory read machine cycle. If the conditions are true, there is no difference. Same for a micro RTL will be same for if true. If condition is false, if false, the memory read machine cycle, the first memory read machine cycle, what will happen in that case? You will have the normal T1, T2, T3. Only in the T3 state, once the condition is checked, if it is false, then PC will be again incremented, because we need to increment PC by one more step. When we are actually reading the least significant bit, the program counter was here. Then in the T2 state of the first memory read machine cycle, program counter was incremented and it will be pointing here. But we are actually now going to skip that memory read machine cycle, the second memory read machine cycle, if the condition is false. We need our program counter to point here so that the next instruction can be executed. So we will increment the program counter twice. In case of the memory read machine cycle, it will be incremented in the T2 state as well as in the T3 state. So in both T2 as well as in T3 state, the program counter will be incremented. If it is false, if it is true, then whatever we had written for jump address, the same will be for this case as well. Number 3, you have call instruction, call ADDR. What does call ADDR do? It will basically load the program counter with the specified address so that next instruction starts from specified address. Now how is it different from the jump instruction then? The return address will be saved on top of the stack. This is top of stack. We have studied the stack memory and we have discussed how we can use stack memory to execute modular programming. It will be furthermore clear with these instructions and with some programming. So what does jump do? So once this instruction is basically executed, if we find out that the condition is true, or even if we do with the normal jump instruction, the program will jump to this address location and start instructions from there. But with call instruction, what it does is it jumps to this location but also saves the return address. That means whatever address is this address will be saved. This particular address will be saved in case of call instruction. And once this instruction is saved, so once this program here is executed, it will return back to this program. In case of jump, it does not return back. In case of call, it basically returns back because this address has been saved on the top of the stack. Therefore, you can write the macro RTL of this instruction as the program counter is loaded with the address and stack pointer. It is 16-bit register. Our address is also 16 bits. N plus 3h. Fine. So we actually defined here that if this was written at if the opcode of the call instruction was written at memory location n, the next instruction will actually start from n plus 3. So we need to actually store this n plus 3 somewhere. So the most significant bit of this is stored in ms plus sp minus 1, and at msp minus 2 the least significant bit of this is stored. Fine. So this is stack memory. At sp minus 1 the most significant bit will be stored. At sp minus 2 the least significant bit will be stored. Fine. So since we are starting from the top of the stack, therefore it is known as the saving at the top of the stack. And sp will be actually loaded with sp minus 2 in this instruction. That means this instruction, this address will now be stored in the stack pointer. So whenever we need to now access the stack pointer, we need to fetch this address location. So it is actually like this: last fill, first out. Fine. Last in, first out. So whatever was filled last, that's actually the least significant bit in this case, that will be fetched first. Fine. That will be actually removed first. So once we are actually saving, we'll be actually saving the MSB of the address first, then the LSB. But once we are actually retrieving back, we'll be retrieving back the LSB first and then the MSB of the address. So this is about this instruction. About its rest of the properties, it's a 3-byte instruction again, and it has 5 machine cycles. Why we have 5 machine cycles? We have an opcode fetch machine cycle. We need to read the address, so there will be 2 machine cycles for reading the address. We also need to write this address on the stack memory, so there will be also 2 write machine cycles, MWRMC, fine. And regarding the number of T states, it has 18 T states. Now if you calculate how these are 18 T states, opcode fetch machine cycle in this case will be having 60 states. The rest of these are having 3 each, so 3 4s are 12 plus 6 is 18 T states. Opcode fetch machine cycle in this case will be having 16 T states, as we have already done previously also one instruction with 16 T states. So therefore the execution time will be 5.76 microseconds. There will be no variation. The example of this is, you can write any example, you can call on anything, call 3300H, fine. So this is some address, IJ, no flag affected, K, the addressing mode, for the source and for the destination. For the source it is direct, it is given to us. For the destination, the addressing mode here is implied. Moving on to the micro RTL. So this is your opcode fetch machine cycle. You have 60 states. So in the T4 state, call ADDR will be equal to 1. And T5 and T6 states, in this case, basically they will be used for loading the stack pointer. SP becomes equal to SP. SP minus 1 is actually loaded onto the stack pointer. So we have to actually, where we are storing the address, we are storing the MSB at SP minus 1. So SP minus 1 needs to be loaded onto the stack pointer, not SP. We do not start with SP from the topmost. One load that stack pointer, fine. Then you have the memory read machine cycle, as we did earlier. In the memory read machine cycle, Z will be loaded. In the second memory read machine cycle, W will be loaded. Now this WZ will not be yet loaded onto the program counter, fine. Then you have the memory write machine cycles, 1, this is 2. In the memory write machine cycle, so this is your, let me clear this page. So this is memory write machine cycle number 1. We do not have HL here. It's actually this is not HL here. This will be SP. Fine. The stack pointer will be loaded onto the address bus, the highest significant bit and the lowest significant bit. Write instruction will be enabled. WR will be equal to this. 1 minute. So this will be the memory write machine cycle in T1 state. SPH will be loaded onto the address bus on the most significant bit. SPL will be loaded onto the address bus and ALE will be enabled. SP will now be decremented so that the next address, we are actually retrieving right now the higher significant bit, the most significant bit, and that will be actually loaded onto the data bus. So during this instruction, the most significant bit of the program counter is actually loaded, and simultaneously the stack pointer has to be decremented so that in the next, whenever the next instruction takes place, it already points to the next location. So this is your memory write machine cycle number 1. Fine. Similarly, in the memory write machine cycle 2, what will happen? Apart from this, only the least significant bit of the program counter will now be decremented here, and this will no longer need to be done in the memory write machine cycle number 2. We do not need to decrement the stack pointer further, and it will be here that the program counter now will be loaded with whatever was on WZ. Fine. We do not need to write that during the memory read machine cycle. We'll now do it at the end of this instruction cycle. So you have 5 machine cycles. Opcode fetch machine cycle. The difference here is it's a 6T state opcode fetch machine cycle. You have the memory read machine cycles. They are similar to what we did in case of jump instruction. Memory write machine cycles. In the first memory write machine cycle, the most significant bit of the program counter of actually n+3 location will be stored on the top of the stack in one memory cycle. In second memory write machine cycle, the least significant bit of the program counter will be stored on the next stack pointer location. So with this way, we are actually able to save the address from where we will be actually executing. Once we return back, we can start from executing the program here. So similarly, you have call conditional address. Fine. So it does the same as we saw in case of jump conditional. So depending upon if the condition is true, then this will happen. If the condition is not true, then we need not do anything. So accordingly, if the condition is true, you'll be having 5 machine cycles. If the condition is false, you'll be having only 2 machine cycles. As I said to you, the condition is checked in the first memory read machine cycle only. If the condition is false, stop there. If the condition is true, continue on. If the condition is true, then you'll be having 18 T states. You'll be having 5.76 microseconds of execution time, 8 variations, and you'll be having 8 variations. Those variations will be call if CZ address, CNZ address, CC address, CNC address, CPO address, CPE address, CP address, CM address. Fine. So these are your different variations. Then you have the same, no flag will be affected. The addressing mode for the source, it is direct addressing mode. For the destination, it is implied. And the so if you have if the condition is true, there will be 5 machine cycles as we had in case of call address, the same 5 machine cycles, no difference. If the condition is false, we'll be having only 2 machine cycles, the opcode fetch machine cycle and the memory read machine cycle. And in the memory read machine cycle only, the program counter will be incremented in both the T2 state as well as in the T3 state. As well as what will happen in this case is that the stack pointer will be reset. Fine. So I'll be actually also loading a PDF describing all these different types of instructions. So we have done 4 instructions so far in this group. 5th instruction is RET, return actually. So what does this instruction do? It loads loads the program counter with the return address fine. So where is this return address? This return address is retrieved from the top of the stack. So call instruction helps us to call an instruction. Now we need to return back to that, return back to our original location. So for that we use the return instruction. So this is similar to jump instruction, not more like similar to jump instruction rather than call instruction. So that next instruction is executed from there. So what will be the macro RTL of this instruction, return instruction? The program counter, the least significant bit, as I said to you, the least significant bit will be retrieved while calling. The the most significant bit was saved first, but while retrieving back, the least significant bit will be retrieved first. And the stack pointer will be reset by putting it back to its original location, that's sp+2. So as far as the instruction goes, it is a single byte instruction. We do not have any address specified here because that address is already at the top of the stack, and that's actually implied here. So the instruction itself is only 1 byte. There is no need to mention, there is no mention of the address in the instruction. So it will also have only 3 machine cycles. You will have the opcode fetch machine cycle, you will have the memory read machine cycle, and you will have another memory read machine cycle. The memory read machine cycle will actually read the address from the stack memory, the least significant bit and the most significant bit. So accordingly you will be having 10 t states. You have a normal opcode fetch machine cycle here, so only 10 t states. You have 3.2 microseconds of execution time. There is no variation. The example is return. The no flag will be affected again in this case. The addressing mode, for the source it is implied, for the destination it is the destination is also implied, the source is also implied in this case. As far as the micro RTL of this goes, you have a normal opcode fetch machine cycle, no difference there. You have the memory read machine cycle and the memory write machine cycle. You have two memory read machine cycles, sorry. You have memory read machine cycle number 1 and you have memory read machine cycle number 2. So what's happening in the memory read and the memory read machine cycles here? So in memory read machine cycle number 1, here, this will be the memory read machine cycle 1 of this instruction. The stack pointer is loaded onto the address bus, and the most significant bit and the least significant bit. SP is incremented here, fine, and whatever was on the data bus, that is actually loaded on as the least significant bit on the program counter, fine. In memory read machine cycle number 2, for this instruction, what will happen? Again, the stack pointer will be loaded onto the address bus. It will be incremented in the second stage. So total SP now it becomes equal to SP+2, and in this case, whatever is on the data bus will be specified as the most significant bit of the program counter, fine. So you have the two memory read machine cycles and the opcode fetch machine cycle of the return instruction. Similarly, your next instruction is return conditional. So if there is a particular case where the condition is true, then it will return. If the condition is not true, then it will not return. So accordingly, you will have different variations of this. You can have RZ, RNZ, RC, RNC, RPE, RPO, RP, and RM. Fine. So checking different flags, whether the 0 is set or not. Parity, carry, auxiliary carry. Fine. So you check these flags accordingly. Then you will be having the micro RTL of this. So as we have discussed so far in the conditional instructions, in the T2 state, in the second machine cycle, that is the first memory read machine cycle, the condition will be checked. But here in this particular case, in this instruction, condition is checked in the opcode fetch machine cycle only. So this is something different from the jump conditional and the call conditional. The condition is checked in the opcode fetch machine cycle only. So there can be either 3 machine cycles if the condition is true, or there can be only 1 machine cycle if the condition is false. So if true, 3 machine cycles, similar machine cycles as we saw in case of return instruction. If false, 1 machine cycle only, and that is the opcode fetch machine cycle. So this is how the return instruction is actually different from the return conditional instruction is different from the jump conditional and the call conditional. Also know that in this case the opcode fetch machine cycle has 6 T states. Fine. So you'll see actually the complete micro RTL in the PDF that will be loaded in the classroom as well. So far we have studied 6. 7th instruction is, now this is slightly different instruction. It is PCHL. So what does this do? Load PC, the program counter, with contents of HL register pair. So in this case, the HL register pair will actually be holding the address, location, and we can load that onto the program counter. There is no address specified here, so it's only single byte. That's the opcode fetch machine cycle. The opcode will consume 1 byte, and it also has only 1 machine cycle because there is nothing to be read from the memory in this case. Only the opcode fetch machine cycle in this case you have. Only thing is that this opcode fetch machine cycle is of 6 T states, not of 4 T states. So accordingly, the execution time will be 1.92 microseconds, and there is no variation. Example of it is only exists as itself, that is PCHL. Just like XCHG, it's a standalone instruction. The addressing mode is implied. Regarding the flags, again no flag will be affected. JKL, the micro RTL, it has only 1 machine cycle, and this machine cycle is of 6 T states. In the T4 state, PCHL instruction will be equal to 1, whereas in the T5 T6 instruction what happens is that this program counter is actually loaded with the HL. The program counter is actually loaded with the contents of the HL register pair and the T5 T6 states of this opcode fetch machine cycle. So this is your instruction number 7. Instruction number 8, you have RSTN. Fine. So this is a so what does this instruction basically do? It is a single byte call instruction. So normally the address is 16 bits, that's 2 bytes, but this is a single byte call instruction. So what it does is loads PC with 8 cross n 16-bit address, so that the next instruction is executed from that particular address. And save return address on the top of stack. So you have this instruction. So what does this instruction do? Using the macro RTL, the program counter is actually loaded with 8 cross n. So what it actually represents here is actually number of different variations of this instruction. So if we have you'll be writing this at memory location n, and at n plus 1 you'll be writing the next instruction. The program counter will actually be loaded with only the 8-bit address. Since we cannot actually load an 8-bit address, so what we do is that the most significant bits in this case are made equal to 0 and 0. The least significant bit is actually what is implying to the 8-bit address in this case. So the program counter is loaded with an 8-bit address, so only it will be an hexadecimal number, and the stack pointer will be carrying the return address, that is the most significant bit of this address and the least significant bit of this address, and SP becomes equal to SP minus 2. So it is the instruction exists only as itself, so it's a single byte instruction, and it has 3 machine cycles. You have one opcode fetch machine cycle, you have an opcode fetch machine cycle, you have a memory write machine cycle. You do not need to read any address because that address will be actually specified within the microprocessor, but you need to store the next memory location on the top of the stack. For that we need 2 memory write machine cycles, so a total execution time of 12 t states. 12 t states because the opcode fetch machine cycle in this case will be of 6 t states f, and therefore 3.84 microseconds. You have 8 variations, and what are these variations? Examples of these variations are, you have RST0, we have written RSTN. Fine. So RST0 is the first one. So this basically means address 0000H, hexadecimal number. RST1 means 0008H. RST2, it basically means 00110H. RST3, it means 0018H. RST4, it means 0020. RST5, RST6, RST7, 0028, 0030, 0038. So these are only addresses that you can actually specify using this instruction. Then you have the no flags will be affected in this case. The addressing mode for the source as well as for the destination, the addressing mode is implied. So